Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads determine the shear and moment as a function of x and then draw the shear and the moment diagrams. This problem is coming from the engineering mechanics statics textbook, 13th edition by R.C. Hibbeler. We have a cantilever beam at A is a fixed support. Therefore, we expect a moment reaction, a horizontal reaction, and a vertical reaction. The cantilever beam is loaded with a triangular distributed load, which has a maximum value of 6 kilonewtons per meter. And the maximum value is at A. So if I was to call this point B, B has 0 while A has a negative 6 kilonewtons per meter. So quickly, let's draw the free body diagram at A. Like we said, we have AY. At B, at A again, at the same A, we have AX. And then we have a clockwise, anti-clockwise moment here, which is just our reaction. Okay. Let's find the equivalent force from this triangular distributed load. So let's say we have the equivalent force, which is located at, remember centroids? So this one is located where? At 1/3 of the length 3, which is equal to 1 meter. And this one, let's call it as F. So this one, let's call it as F, equivalent, which is just equal to the area under the load diagram. So half by the length 3 by the maximum peak, which is 6, and therefore this gives us a 9. Alright, so this load, it is this one there. Great. I'll need also to, because we want to determine the, okay, I'll come and explain that later on. So quickly, let's apply the equations of equilibrium. Summation of moments about point A equal to 0 and clockwise being our reference. What do we have? We have anti-clockwise moment, which is a 9, positive 9 by 1. What else? Plus MA equal to 0. Therefore, our MA is just going to be equal to minus 9 kilonewton meters. Okay. Negative, it just means the sign changes. So the sign will just be like this. Okay. Let's wrap this part here. The sign has changed. Alright. So this is equal to 9 kilonewton meters. Alright. What else? Let's now apply the summation of forces in the y. Summation of forces in the y direction. So we have summation of forces in the y direction equal to 0, going up in our reference. So we'll have minus 9 kilonewtons plus AY equal to 0. Therefore, AY is just going to be equal to 9 kilonewtons. Then we have summation of forces in the x direction equal to 0. We don't have any force in that direction, therefore we expect AX to just be equal to 0. Alright, So here we are now. Let's make a section. And one good part about this beam is the load is continuous from B to A, which makes the problem very easy to handle. So let's make a section there, and then we are going to get that part, which is of course the simplest part. Okay, so we'll have a distributed load like that. Okay, and this point we say is B. And here, if we call this point 1, we're going to have a shear force V1 and the moment M1. So this the equation that governs this loading, we'll need to rewrite it in terms of y is equal to mx plus c. Remember this, the linear equation. Instead of y, we'll say q is equal to mx plus c. We know c is equal to 0. M is the gradient, which is just the change of y divided by the change of x. So the change of q divided by the change of, the change of y, yes, which is the q divided by the change of x. So what is our change of q? It is a 6. Change of x is a 3. So what does this give us? A 2. Therefore q is equal to 2x. So this is our q, equal to 2x. So this is the equation governing our load, okay, which is also a function of x. Okay, so q is a function of x. You can also write it as q of x equal to 2x. All right. Okay, so our q, it is this point here. That is our q. This is our q, okay, which is equal to 2x. Then we are going to have an equivalent force. An equivalent force we are calling F, and it will be at the position. What position is that? That position is 1/3 of x. 1/3 of x, because this whole length for this small segment of this piece of a beam that we've cut is x, moving in that direction like so. So we have all the information, but we've not defined what F is. Therefore, this F, which is an equivalent force on this small segment of the beam that we've sectioned, is going to be equal to the area under the load diagram. So it is going to be half times x times q, which is 2x. Therefore, this gives us what? X squared. Great. So what we now know what this F is. Let's apply the equations of equilibrium. So say summation of moments about point 1 equal to 0, and clockwise being our reference. What do we have? We have this F, okay, this F, which is x squared, x squared times the length or the lever arm, which is 1/3 of x, giving us a positive moment or anti-clockwise, then plus m1 equal to 0. And therefore, our m1, which is a function of x, will be equal to minus x cubed divided by 3. Is that fine? Let's go to the next stage, finding the function that governs shear. So summation of forces in the y direction equal to 0. Again, this is not the order you don't need to always start with moment. You can start with shear, really. It's not always like this. It's all about your preferences. Okay. Right. What do we have? We have minus f, which is x squared, then minus v1 equal to 0. Therefore, v1, which is a function of x, will just be equal to minus x squared. Right. Let's now begin to draw, because we have now the function that governs shear and moment. Shear is quadratic or a polynomial of degree 2, while moment is a polynomial of degree 3. Okay, great. So let's put our line there for our shear and maybe our moment somewhere there. Great. What do we have? We have positive there, negative, we have positive, we have negative. Alright, this is the shear force diagram, and this is the bending moment diagram. So let's start with the shear. Shear is quadratic, okay, and look at the equation. What do you think? When it's negative, okay, before we go to the equation, let's look at the boundary at B. Of course, should have been included it in the equation. You don't have to mind about that. If you've done the equation properly, then you don't have to worry about that. Okay, so look at the equation. This is a quadratic, okay, therefore you know that this is going to open like that. It will open like so. Okay, I prefer using green, for no particular reason, just my preference. Okay, so it's going to open like that, okay, and then close. So this value here, we can plug in what is v1 of 3, v1 of 3. So v1 of 3 is just equal to minus 3 cubed, squared, which is equal to minus 9. So this one here is a 9 kilonewton. Mind you, it's negative. Alright, and then Ay, what did we say Ay is equal to? What did we find Ay? Ay we said is 9 kilonewtons. So they will interact there at A. So we have a minus 9 plus 9. What does it give us? A 0. Therefore, this has to close, right? You have to close the business. The business has to be closed, so that we get the money. We get the money and go shopping. Great, there we go. So this is the minus shear force diagram, right, which is quadratic. And when you look at the slope is increasing in the negative direction. It is increasing, and it makes sense. Look at the loading. The loading is increasing, okay, also in the negative direction, right, from 0 to minus 6. So expect the slope of the shear force to also be increasing. When the loading is increasing, okay, negatively, okay, you expect the slope of the shear force diagram to be increasing. What about bending moment diagram? If the slope of the shear, if a shear itself is increasing in the negative direction, what do you think will be the slope of the bending moment diagram? It is also going to be increasing. This slope will be increasing in the negative direction, right? Yes. All right, we have an equation, and this equation is minus x cubed divided by 3. All right, so at B, what do you expect when x is equal to 0? You expect moment to be equal to 0. And then, so m1 at 0 is 0. And then m1 of 3 is equal to a minus 3 cubed divided by 3, which is 27 divided by 3, that's minus 9 kilonewtons meter. But you see, polynomial of degree what? 3. Alright. So let's draw it. So we'll have something like that. Okay. Oh no. Of course, they are not similar. They are not the same. just my not very good drawing. Okay, so there we go. This one here we say this 9. It's 9 kilonewtons. It's 9 kilonewtons meter negative. And then of course here we expect a closure, right? What did we say here? You have an external or reduction moment of 9 kilonewtons, and this clockwise, but the internal force, if you are to section this beam over the moment, will be positive, all right, or it will be anti-clockwise or counterclockwise. Therefore, you have a closure there like so. Okay, you have a closure of the business so that we get our deal, we get paid. Great. All right, this is also a negative moment. All right, I guess we are done. We found the function that governs the moment there. We also found the function that governs the shear. Okay. All right, let's clean up. So I think this is about it. We've drawn the bending moment diagram, we've drawn the shear force diagram, and we've also done the functions that govern shear as well as moment. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.